Okay, so it's 1:30, so we're gonna get started. Welcome back to the second session of the fourth annual Delaware Watershed Research Conference. Just a few reminders before we get started. One, please remember to keep your microphone on mute unless you're presenting. If you are a presenter, you can unmute yourself when it's time for you to present. Number two, if you have any questions for our speakers, please write them in the chat with the speaker's name and the email address in case we don't get to them at the end of the session. But it is planned to answer questions at the end of the session. Whatever we don't get to, I will make sure they get to the speakers with the correct contact information. Also, speakers, you can answer the question in the chat if you have time, but there's no pressure. I will get them to you if I need to. And number three, our moderator for this session is Elizabeth Watson from the Academy of Natural Sciences. She's going to be introducing everybody and keeping everyone on time. So you should be able to see her at the side of your screen, giving you little warnings, and she may politely interrupt you if you go over. So with that, I hand it over to Beth, and she's going to introduce our first speaker.
Thank you, Catherine. So again, my name is Elizabeth Watson, and I'm a coastal scientist at the Academy of Natural Sciences. I will allow the presentation to go on for 15 minutes, and then when there's 5 minutes remaining, I'll be holding up this sign. This is just a little intro to tell you what to expect if you're a speaker. And I'd like to encourage you to put your questions in the chat in case we have time or don't have time to get to them. If they're in the chat, I can go ahead and call on people to unmute themselves and ask their questions. I'd first like to introduce Lynn Perez, my colleague at the Academy of Natural Sciences. Lynn will be giving a presentation entitled New Approaches to High Resolution Agricultural BMP Modeling in the Delaware River Watershed. Thank you, Lynn.
Thank you, Beth. All right, so with further ado, let's just jump in. The work that I'll be presenting on today is a collaborative project facilitated by myself. I work at the Academy of Natural Sciences. I manage our environmental data science section. But this work is a collaborative effort between the Academy and the College of Computing and Informatics. Together, these two institutions have created a joint partnership called the Drexel Environmental Data Science Group. And our objective is to bridge computational science and environmental science. So again, as Beth mentioned, this project is kind of delving into the new approaches to high resolution Ag BMP modeling in the Delaware River watershed. Next slide. So in this presentation, I'll be running through 4 major sections. The first is kind of jumping into the overall BMP, or best management practice load reduction API. I'll then talk about the 7 major archetypes, or 7 major BMP archetypes that we framed out. I'll focus on one of those archetypes, and that's called the polygon drainage archetype. And then the last section is actually implementing this BMP API into a platform that we use very frequently within the DRWI, and the platform is called FieldDoc. Next slide. So before I jump in, let's just take a step back for a second. What is an API? I have to remind myself that not everyone speaks computer. So an API is an acronym for Application Programming Interface. It's a software intermediary that allows 2 applications to talk to one another. So each time you use an app like Facebook, send an instant message, or check the weather on your phone, you're using an API. So when you use an application on your mobile phone, the application connects to the internet, and then through the internet, it's sending data to what we call a data server. The server retrieves the data, interprets it, does something with it, so it's performing a task or an action, and then it sends that information back to your phone. So the application then interprets the data and presents it to you with the information you wanted in a readable way. I hope that makes sense. Next slide. So the overall project objectives with the BMP load reduction API. This project is based and funded primarily through the Delaware River Watershed Initiative, specifically through what we call the Project Impact Assessment. Our funder for this was the National Fish and Wildlife Foundation, and this tool was developed specifically to assess projects that are happening on the ground within the 8 sub-watershed clusters of the Delaware River Watershed Initiative. Our API focuses primarily on ag BMPs. What I'll be talking about today is very focused on ag BMPs. The next year of our work is focusing on urban stormwater management applications. So what I'll be talking about today is solely around ag BMPs. The whole purpose of this work is to estimate reductions in total nitrogen, total phosphorus, and total suspended solids for BMPs using a spatially explicit modeling approach. We then use our API, as I mentioned before, to generate information inside of the Field Doc platform. And the purpose of this is to create, it's to implement project planning and implement project tracking inside of Field Doc. Why is this significant? What this work has done is it's introduced high resolution automated project level information into DRWI workflows. Next slide. So before I get into the nitty gritty, I just wanted to do an overview of our data sources and models. So we are implementing a USGS NHD Plus high resolution 10-meter data set. We built that off of what we call a digital elevation model. We also implemented a flow direction raster. So this is a data layer that basically tells us where water is flowing. Any calculations that we run in this model are done off of the National Land Cover data set from 2011. The basic model or driver behind the information is coming from the Generalized Watershed Loading Function Enhanced model, otherwise known as MapSheds. This is the model that is implemented inside of Model My Watershed and is the primary model behind the SRAT application as well as the Stream Reach Assessment tool. This is a primary model that we use within the DRWI. In terms of the actual calculations for these BMPs, we are running off of primarily the Chesapeake Bay program and PADEP BMP efficiency coefficients for each of the BMPs that I'll be talking about. Next slide. So I'm going to kind of jump into the meat of the overall architecture here. Our API is broken into 7 major archetypes that I was talking about before. Right now, we've generated about 55 BMPs that fall into these 7 major bins. These 7 major bins are what we call agricultural animal, stream restoration, green stormwater infrastructure, land use change, agricultural land, polygon drainage, and exclusion buffer. Next slide. Just to run through each of these rather quickly and how they work. Agricultural animal calculates the annual animal load in a given HUC 12 and applies a reduction coefficient for the area of interest. Next. We calculate the stream length and for stream restoration, we calculate the stream length and use pounds per feet for reduction coefficients. Next slide. For green stormwater infrastructure, we calculate the loads for developed land using what we call a loaded loading rate, and then reduce these loads using fixed reduction coefficients for RR and ST-BMP types. So this is just looking at urban BMP types. Next is land use change. We calculate what we call the pre and post BMP loads based on land use change in a given area of interest, and then calculate the load reduction as the difference between those two land use types or land use change data sets. Next is agricultural land, where we calculate the cropland or pasture loads available in an area of interest and use the upland loading rates for that area. And then we reduce those loads using a standard reduction coefficient. Next is polygon drainage, where for a defined area of interest, we calculate the acres of different land cover types within that area of interest. So this could be running a calculation off of a buffer or a wetland, and then we apply an upland loading rate to estimate these total loads and then reduce these loads using a fixed reduction coefficient. And last is exclusion buffer. Next slide, sorry. The last is exclusion buffer, where we use the approach that combines reductions from both buffers based on an area that's drained and reduced stream bank erosion. So it's essentially, it's combining 2 of the approaches that I mentioned above, but primarily is functioning off of the polygon drainage option. So next we're looking at the riparian forest buffer archetype, or there's a riparian forest buffer BMP that falls within the polygon drainage archetype. This is essentially how everything is functioning, going from both the UI to our API service back to the UI. A user interacts with FieldDoc and they draw in exactly where their BMP is taking place on the landscape. They then push that information through FieldDoc and it's sent as what we call a BMP API request. For that area of interest, we're then locating the HUC12 that it sits within, and we're determining what the loading rate is by pounds per acre for that area of interest. We then use what we call our watershed APIs. This is a separate service that's running a watershed delineation off of that specific BMP polygon. That information is then sent to a separate service that we have, which is essentially doing a rapid calculation of all the land use that falls within that area of interest, both within that area of interest for the polygon and then all the area that drains to that polygon of interest. So for each pollutant, so this is TNTP TSS, and for each land use type, we calculate the load reduction for the BMP, we sum those reductions over all land use types, and then return the pollutant load reduction. So in this case, these are the NP and TSS are the reduction efficiencies that we're applying here in this calculation to the right. So that reduction information is then sent back with our API to FieldDoc, and then the user is able to review the watershed that was delineated for the polygon of interest, the reduction coefficients, and then the modeled nutrient production for their practice. Next slide. So what I'll be talking about today is kind of it's the two major drivers of how we're able to do this high resolution spatial modeling. I talked about it briefly, but we're running or implementing our watershed API. This is implementing what we call our watershed marching algorithm. And you can look at the visual that I have here on the bottom right corner. So the watershed delineation API uses the watershed marching algorithm, which takes advantage of the fact that a hydrologically conditioned, what we call a D8 flow direction grid, can be represented as a tree to which a modified nested set algorithm can be applied. So for every single question or query or probe, this data structure can determine what flows into a particular node from upstream. So that's saying that for a query that you're asking at this node, at like, let's say the 5 or the 6, you can tell that 7 and 8 are flowing into both 6 and 5. Is it possible for me to use a cursor? Can I like drive on the screen? It would make it much easier for me to explain some stuff.
I don't think it is, but I mean, I can try for you. I have a cursor. If there's something specific you want me to point to.
Okay, it's okay. I thought I would ask. So in this graphic that we are looking at right here, you can see that we use what we call a depth first search to determine the discovery and finish value for each of the nodes that are within that tree. So from there, you can see that, for example, V flows into U, and if and only if the discovery time for V is between the, so V flows into U if and only if the discovery time for V is between the discovery and finish value of U. So from the node with the discovery value of 4, for example, so we're looking at the left square. If we're sitting at the 4 and we march right, and we ask if 24 is between 4 and 23, it's not. And so we then ask if 20 is between 4 and 23, and it is. So we can begin to then build the watershed boundary to the right. And then if you ask the same question again, you can then march up the tree. So this is essentially the mechanism for how we are doing that watershed delineation. We essentially just skirt around the outside. Next slide, please. There we go. So this technique that we were using is much faster than other existing techniques and will scale better with the increasing amount of high resolution raster cells that you have within an area of interest. So for example, if we're going from a 10 meter to a 1 meter data set, the grid processing approach will be 100 times slower, whereas this approach would only be about 10 times slower. So you can see in the graphic on the right, our approach is that red line that's going around the outside. We're asking significantly less questions and having to visit every single raster cell within a watershed of interest. I have 5 minutes. Okay, thank you. So this is important when you're starting to think about the complexity of a watershed of interest. So think about how this might translate to the Chesapeake Bay watershed, or perhaps if you're delineating the Mississippi River watershed. So this kind of speed allows us to ask questions in real time. Next slide, please. We're also able to ask questions not just for a polygon, but we can ask it for a line or a point. That's really the gist of what I wanted to make here. Next slide, please. So jumping to the fast zonal API, this was the step that was after the watershed delineation API. We're implementing what's an algorithm that's essentially called Green's theorem. It's a very old algorithm, and it's a principle from calculus that was developed in the mid-1800s. In short, Green's theorem states that the sum of the forces acting on an object can be calculated by the double integral of the counterclockwise boundary. And so what that essentially means is you can count the values inside by skirting around the outside. And we have a way of pre-processing our data to sum it and then subtract, and it ends up giving you the values that's inside of an area of interest. Next slide, please. So to do this with land cover, first we do a pre-processing of the grid, which is just a cumulative sum down. So you can see that illustrated in both M and F. So by taking the boundary of a polygon that's submitted against this grid, we use the marching algorithm to run counterclockwise and keep track of the total sum by adding while going right and then subtracting while going left. This is what I was mentioning before. So the result of the sum is the raster grid cells within the polygon. Next slide, please. I won't kind of labor on here too much, but the general takeaway from here is as you increase in the number of questions that you're asking of an area of interest, so as your size of an area of an interest increases, older methods, particularly rasterstats, which is the most commonly used method, grows exponentially. The complexity of the question grows exponentially, whereas with our methods, the growth is linear. Next slide, please. So this is just kind of jumping back to the original workflow of the riparian forest buffer example that I was looking at before. I just wanted to refresh folks about where the data starts, how the calculation happens, and where it goes. Next slide, please. It all kind of comes together inside of the user interface, which we were talking about before, and that's FieldDoc. This is just an example, an illustrative example of an area a user draws in, this red polygon area where they would like to put in a riparian forest buffer, and we then run the reduction calculations off of that. So in this case, we have reductions for TNTP and TSS illustrated above. Next slide, please. This is just the last, I think this is the last slide that I have for all of you. It's just, it's a link to our technical documentation. So if you are interested in testing, in testing our API service and or exploring any of the other API services that we have, you're more than welcome to do so. This is the address where you can do that. It goes into full detail about how to ask a question to the API service and how it might be implemented in projects that you have. Next slide. Thank you all.
Thank you very much, Lynn.
Yeah.
So while I guess I would like to invite Laura to unmute herself and ask her question. We have one question in the chat while Catherine is switching to the next presentation.
So you mentioned, Lynn, that you're going to switch to urban settings next, but the land uses are really varied, and the load reductions that are typically programmed in are from very old reports. Do you have any plans to assess those land use relationships or update them when you move to the urban setting?
Yeah, that's a great question. And it's one of the reasons why we delayed rolling out the urban API services. We think that we will be able to leverage the 1 meter land cover data set that the foundation paid for a number of years ago. And we know that we can run our queries off of this much higher resolution data set that's it's updated. It's from just a couple of years ago. And I think that it would increase to the accuracy and be adequate for the questions that you would be asking in an urban setting.
That's not actually my question. Even if we know the land use types, we don't know the loading for these land use types.
Yep.
The data isn't very good.
No, that's absolutely true. And I know that you and I have talked about this before in the past. It's implementing GWLFE or the MapSheds model in an urban context. It's not what it was designed to do. And so we would have to we'd have to have a conversation about how to model each of the urban BMPs. And I also want to add that the calculations that would be happening at a much higher resolution than the rest of the calculations for the BMPs that I mentioned in the chat. So I'm not sure if that clarifies your question. Hopefully it does, but I'm happy to talk to you offline about this as well.
Yeah, thank you.
Absolutely.
Thank you very much, Lynn. I'd like to thank our speaker and move on to the next one. I apologize if I mispronounce this name, but I'd like to introduce Thomas Amidon, who will be giving a presentation entitled Studies to Determine the Attainability of Aquatic Life Uses and Associated Enhanced Dissolved Oxygen Conditions in the Urbanized Portion of the Delaware River Estuary. And before he gets started, I'd like to remind you that we're in a session that goes from 1:30 to 2:50. So there'll be a break at 2:50 and we will reconvene at 3 o'clock. Thank you very much, Thomas.
Nice job with my name. Perfect. Hope everyone's had their afternoon coffee. We'll be talking about dissolved oxygen in the Delaware River Estuary and have a fair amount of ground to cover. This will be a high-level conceptual overview of how DRBC is integrating various studies into a cohesive analysis of attainability, and then zoom in on 2 studies that are funded by the DWRF. Very happy to be here with you. Next slide, sorry. I thought I was controlling my own for a minute. I was agreeing with Nathan at the beginning of the conference when he mentioned cobbling together funding. That's exactly been DRBC's approach. The DWRF has been an indispensable partner for us on this project, and we have a number of other grantors that have helped us piece together the components needed to complete the work. Next slide, please. The two studies we'll be zooming in on. One is modeling eutrophication processes in the Delaware Estuary, the purpose of which is really to relate nutrient loads coming into the estuary with water quality impacts in the estuary. The lead investigators for that are Doctors Namsu Suk and Li Zhang from the Delaware River Basin Commission. And the second one is an engineering evaluation and cost estimation of wastewater treatment nitrogen reductions. That work is essentially a cost estimate to achieve specific nitrogen targets. And the lead investigator is Tim Bradley from Kleinfelder, my former employer. And the project manager is John Yagachek from the Delaware River Basin Commission. Next slide, please. This shows a graphic of the Delaware River Estuary, which I'm sure you know is tidal, all the way from its outlet at River Mile 0 all the way to the head of tide at Trenton. And those lines stretching across it are the zones defined by the DRBC. Zones 2 to 6 are essentially the estuary, the saline portion, the tidal portion. Next slide, please. This shows essentially the urbanized portion, most urbanized portion of that. Whoops, can you go back a slide? Yeah, I wanted to zoom in on that. That the portion that's highlighted there is the urbanized portion from the Philadelphia Camden area to Wilmington area. And that portion is important because it's designated for fish maintenance only rather than maintenance and propagation. As a result, the dissolved oxygen criterion in that area is a daily average of 3.5 milligrams per liter to support maintenance of fish species. And that's approximately river mile. Well, you can see the area, but it's zones zones 3, 4, and part of 5. Now you can go to the next slide. Importantly, when the criteria in that area was established, the designation was essentially aspirational, since the actual dissolved oxygen was not present for long periods of each summer. Really, that was putting a stop even to fish passage. But as you can see from this graph, which shows dissolved oxygen during July at Ben Franklin Bridge over a long history, dissolved oxygen conditions have improved a lot, currently exceed the fish maintenance criterion. And in fact, the maintenance only portion of the estuary currently supports a thriving fishery. And I've shown there some of the DO sensitive species that currently exhibit some degree of propagation in that area. Next slide. So as I pointed out, next slide, please. In response to this reality, the DRBC Resolution 2017-04 envisions a number of studies that are either completed or underway to address this issue. And the first is a series of fish and dissolved oxygen studies. Next slide, please. The second are modeling studies, including the one we're talking about today. And the third, go ahead, next slide, is some cost and feasibility studies. Next slide. So the analysis of attainability that's the core of this resolution really brings together all these studies into a single analysis. Next slide. So what is an analysis of attainability? Well, what we know is that the minimum DO conditions, you can slow that down a little bit, are critical to supporting fish propagation, the minimum DO conditions. We also know that the existing DO condition does support some degree of propagation. And we know that higher minimum dissolved oxygen condition, in other words, more oxygen, will enhance the degree of fish propagation. Next slide. Next, there you go. So the question that's really at the heart of this analysis of attainability is how much can the dissolved oxygen condition be improved? What would the DO condition be under quote background loading conditions? What would they be under various levels of point and non-point source reductions? And ultimately, is it feasible to meet the minimum required DO to support propagation of all those sensitive species? Next slide. And ultimately, what would be the costs and benefits associated with various reduction options? So the DRBC is really about the business here in this project of determining the highest attainable dissolved oxygen condition, which will then dictate the associated designated uses. Next slide. So this is how we see the elements coming together. First of all, this point source nutrient reduction cost evaluation will give us a sense for what's technically feasible and financially what will be involved with various scenarios of treated effluent improvements. The levels that we've studied are shown there. I'll get into that in a minute. Next slide. The next piece is a tool to relate nutrient loads coming into the estuary with water quality results in the estuary, in particular dissolved oxygen conditions. So that's where the eutrophication model comes in. How much would the dissolved oxygen condition improve under various reduction scenarios? Next slide. So we see this as being able to present both costs and benefits to our commission. And of course, benefits you can measure in terms of increased dissolved oxygen. You can also measure in terms of increased full support of propagation, and for that matter, increased estuary value. Attainability relates not just to cost, of course, but to natural condition, technological limitations, et cetera. Next slide, please. So this is a significant undertaking. The graphics here show the grid for the system-wide eutrophication model. The different colors on that map are different numbers of vertical layers. And then there's a zoom in on that for a particular portion of the estuary. Yeah, just hang there for just a minute, Catherine, thanks. I'll be quick. So ultimately, the modeling approach is to link EFDC, which is in this context is used as a fluid dynamics hydrodynamic model, with WASP, which is a widely accepted water quality tool. Each of the bullets here that I've listed are in and of themselves significant undertakings. Many of them are individually grant supported. I'm not going to go through every one of them. Ultimately, the goal here is to be able to, at the bottom, conduct forecast simulations with a calibrated model to be able to, that would involve one, determining a baseline condition, and then looking at different levels of external sources to achieve specific levels of dissolved oxygen. Next slide. The hydrodynamic model, this is a major accomplishment for 2020. Our expert panel, quoted them down there. They came away with the May, after our May meeting, saying that the hydrodynamic model is adequately calibrated for use in the water quality model. The calibration periods for this are 2018 and 2019, and I will mention that 2012 was added, and that is no small addition. That is an enormous addition to the scope of the project. It was necessary because 2018 and 2019 did not end up presenting a full range of hydrologic conditions. Those were fairly wet years. So we drew in 2012, even though we didn't quite have the degree of information as we did for 2018 and 2019, but it was really to capture a more representative range and those low flow conditions in particular. This achievement also involved several significant improvements to boundary assignments, temperature assignments for all the different tributaries based on a separate analysis that was performed, and then also a statistical model that was developed to assign flows to ungauged tributaries was also developed. Next slide. Oh, yeah, next slide, that's fine. In terms of water quality model development, the field sampling for this is completed. Field sampling was completed, began in 2017, and and continued really right up until the pandemic hit, and then we've begun to take a couple samples since then. But for the most part, the field sampling that will be integrated into the model is completed. Significant progress in model integration has occurred. This has been lots of accomplishments in the water quality model this year. There was we performed an evaluation of vertical resolution to determine how many layers are necessary to capture gradients and mass transfer in the system. And also developed a statistical submodel that estimates water quality at unmonitored tributaries and watersheds, and a detailed methodology to relate the items that are measured at boundaries, such as tributaries and point sources, to actual state variable assignments. None of these tasks are trivial. There's been a lot of work done. The graphs you see on the right, the one that shows all the different sub-watersheds, that is from the tool developed to assign boundaries to unmonitored tributaries and watersheds. And then one of the significant efforts in water quality development has been the development of pre and post processing tools. And so these other graphs are just representative graphs. Don't pay attention to, they're more or less test runs, but they show the kinds of output that we'll be able to show. So for example, the one with the blue and the red dots there is looking at the x-axis is actually river miles, and then the y-axis is concentration values. So it's zooming in at a particular time in the navigation channel, for example. So there's lots of different ways to look at data, and we're developing tools to be able to zoom in on those. Next, in the interest of time, next slide. This comes in. Can you hit play for that? There you go. This is just an animation. It's an example of a post-processing tool. John Yagachek from our office actually put this together with our model output from a particular scenario. And the right to left again is river mile, and then the y-axis is water column, actually water column depth, and then the different colors are dissolved oxygen results over time. So that's a pretty slick tool. This just gives you a sense for the kind of work that's been happening behind the scenes here. Next slide. The nitrogen reduction cost study looked at 4 effluent levels. An ammonia level of 10 milligrams per liter, an ammonia level of 5 milligrams per liter, an ammonia level of 1.5 milligrams per liter, which is essentially considered, at least right now, that's considered the technological limit. And then also a limitation for total nitrogen of 4. So the idea here, if you remember your nitrogen cycle, is a wastewater system will have a lot of ammonia, which can be converted to nitrate in the presence of oxygen. So that's how these different ammonia reductions would occur. But that nitrate is still part of total nitrogen. So getting a total nitrogen down to 4 would involve first converting the ammonia to nitrate and then removing the nitrate through denitrification, significant effort. Next slide. This shows the results from that study. There's a lot of results to show, but I'm trying to get to the heart of the matter here. The study was really focused on 12 plants that represent about 95% of the nitrogen load to the system. And you can see that there are different kinds of plants. There's activated sludge plants, there's activated sludge plants that use pure oxygen, and then there's fixed film reactors. Cost factors that were considered, this is a very significant study. It included not just the capital costs, but also operation and maintenance costs one by one, down to staffing, chemicals, increased energy, management of sludge, and then evaluated these costs in terms of total present worth and annualized present cost. This graph shows one way to show the results. So the x-axis is the effluent ammonia concentration. Okay, and then the y-axis is total annualized cost. That's makes assumptions about loans and whatnot. And you can see that to get the levels from 10 down to 5 down to 1.5 milligrams per liter of ammonia are fairly linear. In other words, the costs increased linearly approximately. And that kind of makes sense because really you're doing the same thing. It's just a matter of how much of the effluent has to be go through that additional treatment. So that's why that shows that way. And then the big jump in cost is the addition of denitrification to get to a total nitrogen effluent value. And that, so this dollars are on the y-axis.
I think you nodded at me, but I wanted to let you know you have 2 minutes remaining.
Yeah, that's perfect. I'm right on schedule, believe it or not. I must have had enough coffee today, I guess, to get through this. So the total present worth costs, capital and O&M for these top 12 plants range, depending on the effluent level you choose, range from 1.1 to $5.5 billion total. Okay, now you can advance to the next slide. I took out a few, Catherine, just in order to be able to get to this 20 minutes. So that's all I have. I've listed some of the resources, the link to the Water Quality Advisory Committee, which has been deeply involved in all of this work, as well as the DRBC's various email groups are provided there, and the contacts for the various projects associated with this are Nam-Soo Sook, myself, and John Yagacek. And Nam-Soo is the Director of Water Quality Science Management. Thank you very much.
Thank you. So while Catherine changes the slides, I'd like to ask a question. So what are the ecological benefits of that lower TN value versus a criteria that's related to total nitrogen versus ammonium? I could see the financial cost, right? But do you
Right.
have an idea about how that affects ecosystems? And I apologize, there is another question in the chat as well, but I think this is all we have time for.
Right. Well, the answer is that we certainly will be able to look at the impact of removing nitrogen on dissolved oxygen, and we'll be able to evaluate the impact of removing nitrogen on chlorophyll A, on phytoplankton production within the estuary. So I guess that's the shortest way to answer your question. Really, the focus, we don't have endpoints beyond that, but we certainly would be able to know whether you'd expect that the most sensitive part of the system to a change in total nitrogen would in fact be phytoplankton production. So we will be able to assess that. If there are other secondary impacts after that, if there's a major change in phytoplankton, then we could possibly be in a position to consider other less direct impacts from total nitrogen. Hope that answers the question.
Yeah, thanks very much. I think we need to move on to the next
Sure.
presenter. So thank you very much for your presentation. I appreciate it. And there is a question in the chat for you to answer in the chat or to get back to later. I'd like to introduce Dr. Claire Jantz. The presentation is entitled, How Will Forest Ecosystems and Hydrologic Processes in the Delaware River Basin Be Affected by Climate and Land Cover Change? Thank you, Claire.
Thanks, everyone. And I'm glad to be here. Let's go ahead and just dive into the next slide, because I am presenting on behalf of a number of team members. And this work that I'm going to be talking about is the end product of a 3-year plus a little funded project through the Delaware River Watershed Fund. And so we've done presentations previously on different pieces of this work, but this presentation kind of gives the big picture. So if we go to the next slide, what we did in this work was to take models of hydrology, tree species, and water runoff, and couple those with models of climate change and land use change to generate estimates of a suite of hydroclimatic variables, to look at magnitude of future floods and droughts. We looked at forest fragmentation, changes in tree species distribution, and a number of other things. And so again, I'm going to be kind of focusing in on the key data products and findings from all of this work. And throughout the presentation, you'll see tags to different websites on our DRB project page where you can get more information. So I just popped those into the chat so you have them for reference. So let's go ahead to the next slide. And I'll cover first our findings related to hydroclimatology. And this work was led by Tim Hawkins. And and he pulled together, this work is driven by climate projections from the CMIP-5 suite of data products under a number of different scenarios of climate change into the future. And then he developed a gridded hydroclimatic model to estimate things like temperature and precip changes in the Delaware River Basin, but also looking at a number of other derivative variables. So what we found here and what you're looking at on the side is a series of graphs that are in a publication that you can find on our documents page, showing the trends for some of these variables at the basin level, so across the whole Delaware River Basin. He found an annual increase in temperature from 2 to 5.5 degrees Celsius, depending on the climate change scenario. Precipitation, rainfall, runoff, and evapotranspiration are also expected to increase, while snowfall, snow melt, and subsurface moisture are projected to decrease. He found, looking specifically at issues related to drought, that summer subsurface moisture could decrease 7 to 18%, and winter runoff could increase 15 to 43%. So this is kind of at the basin scale. If we look at the next slide, and I'm sorry that this will probably hurt your eyes. The other thing with his gridded model, this was run at 1 kilometer grid cells. So he was also able to map out and identify pretty significant heterogeneity and how those basin-wide patterns would play off across the Delaware River Basin. And if we go to the next slide, just as one example, this is looking at changes, at potential changes in winter snow cover. And going from left to right, we're going from sort of current day to the future under a resource concentration pathway scenario 2.5 on the top and 8.5 on the bottom. And you can see, again, sort of a decrease in winter snow melt, particularly in the high emissions scenario on the bottom. So again, I encourage you to, if you want to dive into the details, to go to our document page and look this paper up. Another thing to point out is that with funding through a land protection impact assessment grant from OSI, we were able to also incorporate future climate scenarios into Model My Watershed. So for those of you who use Model My Watershed, you can now take a look at different temperature and precipitation patterns across the basin that came out of this work. Okay, so next slide, we'll take a look at what Christopher Voltamata found relative to historic and future flooding. And in this study, he identified 5 representative watersheds that you can see identified here on the map. These watersheds were selected partly to capture heterogeneity of land use and land cover dynamics, to capture dynamics related to temperature and precip. And also these watersheds are connected to relatively long water gauge data sets so that he could parameterize the HEC HMS model. So he actually put together a really nice summary of historic events that you can find in this paper. But then if we go to the next slide, he also incorporated, he synthesized future land use projections and future climate projections to look at the impact on flooding, and was actually able to parse out the effects of looking just at climate, looking just at land use, and then the synergistic effects of those. So if we look at just climate, he found that the range of change in peak discharge for individual flood events range from a decrease of 6% to an increase of 58%, depending on the watershed and the scenario that you're looking at. Also, increases in peak discharge averaged across all modeled flood events range from 7% to 44% across those 5 watersheds. And looking at these graphs, the dots are showing discharge on the vertical axis, and the horizontal axis are the flood frequency intervals. And so you see the most dramatic changes at the kind of low intensity, high frequency events, which is something to kind of a take home lesson, I guess, for planning and policy. In the next slide, he summed up the impacts due just to projected land use change, where land use change has a smaller effect, up to 10% increase in peak flood discharge, especially in watersheds like the Lehigh River Valley, which is where you see the bigger bars there, because of the pretty dramatic land use change that's happened there, both historically and projected into the future. And then if we look at the combined effects of those on the next slide, we can see that sort of looking at those two things together, we see an up to 66% increase in peak flood discharge and an up to 44% increase in runoff volume. Again, depending on the scenario and on the watershed. And again, feel free to take a deeper dive into this work in this publication that's listed here, and you can find more information about it on our documents page. So moving on to tree species modeling. This is work that was led by Patrick Jantz, who's my younger brother, actually, who's based out at Northern Arizona University. And he specializes in sort of habitat modeling for tree species. What we're looking at here is an example for the eastern hemlock, where sort of looking at the current day distribution of the density of this particular tree species, the suitability historically, and what the future suitability might look like. So under these different scenarios of climate change, we could see differences in suitable places for our eastern native tree species. One of the things that Patrick tried to do, if we go to the next slide, was to actually improve the tree species habitat models by incorporating work from the hydroclimatic models. And what he found is that measures of energy, so things like temperature, potential evapotranspiration, potential solar radiation, which are output from Tim's model, and also seasonal variability and energy and aridity became the most important predictor variables. So these were variables that are not typically available from sort of basic climate models, but that Tim was able to generate from his hydroclimate models. And these variables seem to be, quote unquote, more important for trees, and so help to improve the tree species modeling. Again, we have some more information on this work at our presentations link. So going into land use, so next slide. We have recently actually just released our DRB 2100 projections of land use change that you can find on our products page. And in our land use change modeling, we modeled two different future scenarios. One that we call the Sinners scenario, where we have pretty strong conservation efforts, more compact growth occurring around existing urban centers. The graph on the right is showing one of our key drivers, which is population change. And you can see that we model a more modest level of population change in the Sinners scenario. The corridor scenario, we model a higher than average or a higher than baseline level of population growth. And instead of being compact, that growth is kind of sprawled along major transportation corridors. For each of these two scenarios, we also explored a what if scenario to consider the value of protected lands in the Delaware River Basin. So we ran a scenario where we incorporated protected lands as usual, and then we removed those protected lands to see how that would influence future land use patterns. So if we go to the next slide, you can see that this is kind of our projected development under the corridors and centers scenarios. And in the next slide, this is summaries of those scenarios for urban development. Actually, this is just for the corridor scenario. On the left is our starting point, which is 2011. And we're looking at % urban in HUC 12 watersheds. The middle map is the corridor scenario, so our high growth scenario in 2100. And the right-hand map is how development patterns shift a little bit when we remove protected lands. So basically development, with and without protected lands, when we remove protected lands, development kind of eats up the smaller, more vulnerable open spaces, parks, and protected areas that are closer to urban and suburban centers of growth. These data are also available in Model My Watershed for both visualization and analysis. And so again, if you're a Model My Watershed user, you can check in on that and see these. We also have a series of web maps that you can also explore that are available on our products page. And Lynn's fast zonal API is working in the background if you use these for Model My Watershed analyses. I'm going to ask you to skip forward the next couple of slides just in the interest of time. One more. Okay, so I wanted to make sure I had enough time to cover the forest fragmentation work as well. So with our forecasts of urban development, we were also able to look at impacts on forest. And so we looked at impacts on overall, on how forest was affected, both in terms of overall quantity, but also in terms of pattern. Thank you, Beth. So we used a pattern analysis software called MSPA. And if we go to the next slide, after analyzing patterns of forest cover and changes in forest cover across the basin, what we wanted to do was to develop an index that was ecologically meaningful in terms of assessing changes in forest patterns. So something like a core area would be weighted higher because it had higher ecological value than something like edge. The problem is that making comparisons across a landscape that's as heterogeneous as the Delaware River Basin is a challenge. So in the next slide, what the approach that we took was to actually develop a new metric that allows us to compare actual fragmentation with expected fragmentation. And in the next slide, I think hopefully you'll see what I mean. If we look at the far right, this is a landscape that is heavily forested, but it has different degrees of fragmentation, where it's less fragmented on the top, there's more core area, less edge, and more fragmented at the bottom. And so the new metric that we developed allows us to distinguish between those three landscapes that are highlighted in A, or the three landscapes in B, or the two in C. So using this metric, if we go to the next slide, we looked at how forests could be impacted by future development. That's the map on the right. Another key driver of forest fragmentation in the Delaware River Basin is also energy infrastructure development. And so what we're looking at here is a map showing our fragmentation metric values. Where it's blue, it is more fragmented than what we would expect. And so the map on the left is showing energy infrastructure impacts. And so you can see that the most impacts from energy infrastructure are more in the heavily forested areas of the northern basin. The map on the right is showing impacts from urbanization. So where it's blue, it's more fragmented than expected. Where it's red, it's less fragmented than expected. And these red watersheds that are sort of popping up in the right-hand map are actually indicating coalescence of forests that are occurring as forests are removed. Again, we're actually working on a paper to write these results up, but we do have a presentation available on our presentations page. So that is all. If you go to the next slide, that has my contact information on it, and the links are in the chat. So thank you very much for your time and attention.
Thank you, Claire. Does anyone have any questions? You could feel free to unmute yourself or to put it in the chat while Catherine switches to the final presentation in this section. I was really interested in the MSPA approach to analyzing fragmentation. And so I was going to ask you if you had a paper in press or anything like that, but then you already answered that question. So
Yeah, no, we're working on it. In the meantime, we have like a presentation that we did for the International Association of Landscape Ecology, but that MSPA tool, we didn't develop that. That is one that is already has many papers associated with it. So you can easily track down more information about that.
Is it a software or a package or an R package? Or?
It's a standalone piece of software, but it takes in data from GIS.
Okay, great.
Yeah.
Thank you very much.
Yeah, thanks.
We're going to switch to the final presentation of this session. So again, we're going to end at 2:50 and there'll be a 10-minute break and we'll start again at 3. I'd like to introduce our final speaker, Marie Kurz, who will be giving a presentation entitled Controls on Spatiotemporal Patterns in Water Quality in the Delaware River Watershed.
Thank you all. And I have my instructions, end on time so you guys can get to break. So thank you all for being here today and sticking around. So I want to acknowledge first off my co-authors. This is a real team effort. Myself, obviously a lot of the team involved in the Delaware River Watershed Initiative, where much of this data is coming from. And I also pulled some results from a study that I've been doing with a group we call the Leverhulme Network that has been sort of spearheaded by Adam Ward, Jay Czarnecki, and well, about 40 or so other participants. So I should acknowledge them as well in this. Next slide, please. Right, I don't have control. So I think this is preaching to the choir, but as many of you guys know, this work is coming out of the Delaware River Watershed Initiative that I'm going to present, which has the overall goal of protecting and restoring local water quality and ecological health in the Delaware River Basin, targeting 4 key stressors: ag and stormwater runoff, forest fragmentation, and an aquifer depletion, which, as we often do, I'm not going to be discussing today. And there are an innumerable, I could scroll down that whole list of icons forever. There's an innumerable number of partners who have been contributing data, insight, know-how, and obviously the conservation powerhouse for all this, and funded, of course, by William Penn Foundation. Next slide. So from the scientific side, and as the water quality sort of expert, I guess, at the Academy, I lead the biogeochemistry section there. We come at the science side of this, or the data side of this, with 2 major objectives. The first is to build up our baseline data on water quality and ecosystem conditions across the watershed, try and understand what is controlling those patterns, and then how can we relate that to our work, which takes objective 2 is to inform the on-the-ground efforts and planning. Thinking of things of how does nutrient reduction in a stream actually lead to changes in stream ecosystem integrity? How do stream systems respond to a single or a suite of various BMPs or to preservation? And what is the effect of a whole host of other things like lag times, especially where we do some action on the ground? How long before we actually see a change in water quality or ecosystem integrity? And so that leads to a couple key overarching questions. The first is, what watershed conditions control water quality and ecosystem structure? By conditions, I mean things like the geology, the land use, the morphology of the stream, a whole host of physical, biological, and chemical factors. The second question is, how does water quality and ecosystem structure respond to those on the ground conservation actions? And third is, how can our monitoring results help inform the DRWI and similar work in the future? You've already heard a number of talks touching on this third one. Next slide. So when it comes to actually measuring impact, this is a ton of monitoring work that's been going on since 2013. It precedes my time in this project. And we're doing this at a number of different scales. So it's across the basin. You can see here a map of the basin in its entirety, the clusters, for those of you that know them, highlighted, and a number, well, not, I won't even say all, but most of our major monitoring sites. At the sort of regional level, so looking at larger streams, sort of more integrative sites, which is exactly what we call them, we have 35 sites that we've monitored quarterly since 2013 for water chemistry, also various biological indicators and habitat. That's our most robust data set. We also have more local sites at the focus areas, for those of you who know those, that have been started in the last few years. These have various different frequencies and various different parameters that have been monitored. And then actually decreasingly, we're also assessing project sites. So really sites really close to projects that have been put on the ground and trying to understand the impact there. Again, various timeframes, various frequencies, and various indicators monitored. If you look just at our integrative sites, so that really core data set that I'm going to stress a lot today, I'll just show you here on the left is a map of land use, just, you know, percent land use. Dark green is forest, light green is ag, yellow is ag, or sorry, yellow is developed lands. That's a pattern, color pattern I'll stick with. And you can see that those core 35 sites span a pretty nice gradient of forest versus ag and developed, although you can see there's certainly 4 sites in upstream Philadelphia make up the bulk of our really highly developed sites. Next slide. So getting into some of the chemistry data that we have to date, if you want to know more about the ecology, stick around. Steph will be discussing that, I think, right after the break. So what do we see? What have we started? We've got, you know, going on 5-6 years of data now. Not surprisingly, we see really clear regional patterns in major ions. I started with those due to the expected things: geology, the geography, the land cover. So particularly, I know as interest of road salts are always an interesting topic for a number of our partners. The top right plot is a, basically it looks at dominant chemistry. So not the total concentration of any ion, but what if of the ions in the system, which ions dominate. And for those of you who don't read these frequently, Piper plots, I've broken out 3 colored areas. You can see dots or anything within that blue NaCl signal. Those are sites, their chemistry is dominated by sodium and chloride, which often most of you know that is table salt. And not surprising, or maybe surprisingly, it was a bit to me, that's usually anything in that box typically is a seawater signal, so coastal sites. But in our case, it's the Poconos and the Upper Lehigh sites, those purple and blue dots. And this probably reflects the predominant source of, or a large source of major ions to these systems is crystalline road salt application within those mountainous areas. If you shift upwards into this magnesium chloride, you'll see a lot of brown dots. That's the upstream Philadelphia, or really developed sites. And the pellet salt that you often see applied around the city. So salt isn't always just sodium chloride, it can also be magnesium chloride. And so we may be seeing a signal of that sort of different chemistry that's often applied to salts within urban environments. And then that geology signal comes out really nicely in that gray calcium carbonate. So calcium and carbonate, that's limestone. So not surprisingly at all, the yellow and the green, those are our karst sites within the Middle Schuylkill and the New Jersey Highlands area. So really nice patterns that we'd expect there. Also looking, you start to see some land cover patterns. If you look on the bottom, this is just binned out the concentrations of chloride in our dominantly forested, ag, developed, or mixed land use sites, so dominantly being more than 50% in the singular land cover, across the different seasons. But you can see yellow, the developed sites, always are highest in terms of their chloride concentrations. And I'll touch on those seasonal signals in a little bit. Next slide. So piggybacking on some work that Steph did, looking at some primary component analysis, not surprisingly, you see land use fall out really clearly here. So I've sort of binned, again, you have a lot of indicators that fall out around that forest signal, a lot around the ag on the bottom right in light green, including major nutrients, and then a sort of a bin of parameters falling out around that developed, including the sodium and chloride signal that we just saw. Next slide. So digging a little bit into sort of the why, so nutrients, as we just saw, and are not surprisingly, are broadly correlated to land cover. And the strongest correlation for the nutrients and for most parameters actually comes from percent forest, which is slightly stronger or slightly more explanatory than percent natural. So if you take any sort of forest, wetland, open areas, and then those are stronger than ag. And on the bottom left, you can see, I just put a little plot for those of you like looking at R squares, as well as plus or minus, just to give you a sense of it's a positive or negative correlation. The top right plot shows that forest versus total nitrogen, and this is the average for the sites. The large dots are our integrative sites, so this most robust data set. The smaller dots are any other site, which often could be just a single data point, which is why I rely a little less on those. Note also both of these, TN on the top and total phosphorus on the bottom, are in a log scale. So these are exponential regressions that we're looking at here. We see, so total nitrogen, this is quite strong, phosphorus less so, total suspended solids or suspended sediment, sorry, less. And really, we don't see these clear signals in much more than these sort of really major parameters, which is interesting because that says that there are, not surprisingly, the other controls, of which there are a multitude on various chemical factors within a stream, be it the riparian land cover, the BMPs, the ag type, these sort of nuances and these confounding controls really start to mask the signal when you get beyond these sort of primary parameters of nutrients, chloride, and sediment. Even in sediment, it starts to get tricky. We also have to consider, obviously, there's a lot of covariate impacts, which we're sort of still digging into. Interestingly, I don't have a graph showing this, or I didn't include it, when you take that forest versus total nitrogen relationship and you look at the residuals of that, we actually see that forested land cover becomes the strongest predictor of nitrogen, at least in large catchments. Indicating that there's sort of an integration, a scale dependency in our sites that we need to consider. And not surprisingly, when you look at those residuals there, you also really clearly see the influence of ag and developed, where with increasing ag and developed, you still see increasing major nutrients, especially nitrogen. Again, nitrogen always being the clearest signal. Next slide. So digging a little bit more into some of the nuances. So the top right here, this is normalized, basin normalized total nitrogen concentrations against catchment size. So this is essentially what is the average nitrogen concentration of all of our sites, of all of our data points, and then normalize every single measurement to that absolute average concentration. And so if you look at this, that says anything that's plotting up at 10, that means that that point, and each dot on here is a single sample, that point is 10 times higher than the basin average. Anything at 0.1 is 10 times less than the basin average, 10 times lower than the basin average. And so you can see a couple interesting things here. This is also, just the integrative sites. So just looking at the key 35 sites. This is against land use. So we see, if you'll notice that the gray, the mixed land use that have less than 50% of any individual land cover, those all fall out right along that one line. So they're right around the basin average. And that makes sense because mixed land use catchments, they're going to have a more heterogeneous scale. And so that comes out more around average. Note also that the larger catchments all tend to also fall along that one line. So even when a catchment has a singular land cover, like the green forested ones, when they're large, you still get a scale integration effect, which is quite interesting that comes out even despite land use or land cover, excuse me. We also see on here the spread. So each essentially vertical line of dots is a site, and you're looking at all the samples that we have at that site. And if you'll notice, there's a lot broader spread in the dark green, those forested sites sort of in the bottom, because they're typically lower. Forested sites have lower nitrogen than the basin average, but they also have more variance. And then the light green dots on the sort of top, higher than basin average, and those ag sites, those dots are also a lot tighter together, the spread of them, showing there's a lot less variance. And I'll touch on that in just a second. We also, on the bottom, I've shown a plot of total nitrogen concentrations against chloride concentrations. Here you can see there's sort of the main spread is the dark green and the yellow, the developed and the the developed and the forest sites. You see sort of a general spread there. But the ag sites really fall out here, where you see a large spread in the various, sort of point by point concentrations of total nitrogen relative to the spread in chloride. So this says a couple of things, that total nitrogen, certainly in ag sites, there's a lot greater spread of nitrogen concentrations in export than there is of chloride, which is not so surprising that, say, in developed sites, because of that salt application, we'll see more. But that says that there's a lot more, total nitrogen export is much more strongly controlled in the hydrologic, by hydrologic processes in these forest catchments than it is by the ag. The notes on the slide are wrong there. And also that we see much lower temporal variability relative to that chloride. So a nice sort of way of summarizing it, next slide, for all this is to look at within site temporal variance. And so this is, the coefficient of variation essentially of total nitrogen. I see that, thanks Beth. Relative, in this case, I picked forested land use. And then you can see that we have much higher variance in the forested sites, much lower variance in the developed and the ag sites. So this tells us, this is consistent with some of the plots we've already seen. It shows that in forested sites, total nitrogen export is more variable, meaning it's probably sensitive to hydrologic and other forcing, just like we saw with the chloride graph. And it means that in ag sites, export is more stable. And this is indicative of essentially saturated landscape. So no matter what you do to this landscape, nitrogen just keeps coming out, which is really key for restoration, because this says that also no matter what restoration measures you're going to do, there's probably going to be a lot of nitrogen stocked up in that landscape that is going to take a long time to come out. So that's going to result in really long lag times between action and response in water quality. Based on the variance we see to date. I should also know, I forgot, this is all base flow data. So I know Laura especially probably is thinking, what about the storm flow? This is not storm flow data. This is just base flow variation. So with my last 5 minutes, I'm going to skip. Will you go to slide, one more? Yeah, so we've seen, oh, sorry, no, back that one, yeah. So a little spoiler alert. I'm not going to go through the seasonal trends. That's what I just skipped. We also saw, unfortunately, we've seen yet to date, no significant trends in improvement as a result of conservation activities, which is always the first. Have we seen change? No, we haven't seen a statistically significant change over time. But this variance becomes interesting as we can use that to try and understand what will measurable change look like when it finally occurs. What is a significant signal through all the noise that you get in chemistry? And so we've used on the top left there is just a trend of concentrate the standard deviation. So the variance of concentration against any particular concentration. So there's essentially the higher a concentration is, the more variance you get in that. And we can use that sort of one standard deviation threshold as a way of defining what is the window that you need to exceed, either high or low, for something to be considered a statistically significant trend, i.e. a measurable trend. And so we've used the first three, actually now even the first 4 years of data that we've collected at all of those integrative sites, so 4 seasonal samples a year, to establish that relationship. And then you can do this at an individual site. So on the bottom right, for example, is one site looking at total nitrogen and total phosphorus concentrations over time. And that sort of fuzzy area around them shows that one standard deviation threshold, 2 minutes, got it, Beth, relative to concentration. And we're essentially waiting for that dashed line, the average or the running 4-point average, the running average annual concentration, to fall below or hopefully not exceed above that one standard deviation threshold. So that's for a specific site. You can also take that general relationship, next slide, and look at this over any site. And we've done that, and it's gotten integrated into some of the work that Lynn and their group has done, looking at, for any given site with a given concentration, what is one standard deviation below that relationship? And therefore, that's sort of our measurable threshold for any projection of change. Next slide. So if you take any, so if you start to say, well, given how many BMPs we're implementing in a watershed, we have some trajectory of change that we expect based on that. And then what is that measurable threshold? And so this is, for example, the focus area evaluation tool where this got hardwired in. You can click on any NHD plus catchment and it'll tell you how many acres of BMPs have to be converted to create measurable change. And now, because I definitely misjudged my time, I'm going to skip, let's see, one interesting result. I want to share one more. Catherine, can you go one more slide? Is a study, this is pulling in other colleagues. We did a similar synoptic study where we had a single 5th order catchment. We had, I think it was about 40, 50 sites at this catchment, and we had a ton of biological, physical, chemical parameters that we sampled. So it's sort of similar to the DRWI data set, but different in some key ways. Besides the traditional PCA, which if you skip forward, Catherine, I'm going to skip those results. We did some semi-variogram analysis, also going to skip that. The one I want to highlight here, next one, is this one. Oh, no, back one. There we go. So in addition to some statistical, sort of more traditional statistical approaches, we also have been trying out something called support vector machine regression. And basically, this is looking at how do variables relate to each other. Where the ribbons, so these are clusters of variables: physical chemistry, nutrients, macroinvertebrates, the geology, the geomorphology, all these bins. The ribbons introduce or indicate interaction between these groups. So the thicker the ribbon, the more interaction there is between these different groups of physiochemical variables that we collected. And what this shows is that all groups of variables contribute unique information to our understanding of this system, and that over 80% of individual variables could not be predicted accurately without knowing something outside of that group. So we can't, for example, predict a chemistry variable with only other chemistry. It takes something else besides that's out of that sort of traditional group. Yep. Anyway, so this just shows that the key importance of inter and multidisciplinary data, non-group data, which we're doing here, we have biological, chemical, physical, is really key. And I'm looking forward to applying this to, is the next step, what I'm working on now, to the DRWI data to see what we can distinguish as a result. Thank you, Beth. That's it. I'll end there.
Thanks. So I'd like to thank Marie for her presentation, and I really didn't want to interrupt this map. This is
Good that you did.
I think it's really important that we have a little break. So we have a break scheduled now until 3 o'clock to kind of combat Zoom fatigue. But I want to encourage you to put your questions for Marie in the chat, and she can answer them there. Thank you. See you at 3.